Hello, everyone. We're going to be working out this problem in this video, so let's check this out. For the first part, we're going to find the Maclaurin series of this function f of x. Here's our f of x. And then we'll do part B and C related to A. Now, before I begin the video, I do want to mention that you should be familiar with what is a Maclaurin series. And you should also be familiar with the alternating series estimation theorem. Those two things are very important to proceed to do this example. I'll leave some related link in the description box so you can check those out. Let's go ahead and dive into the video. So for the first problem, since it is the Maclaurin series, that means we're going to center at x not equal 0. So when you have your power series, you centered at some x naught. Maclaurin series means the center is actually 0. So I'm going to go ahead and rewrite f of x. So for part A, we can write f of x in this form. We have 1 over 1 plus 2x. So I just rearranged the terms in the denominator. You want to write this in this particular form. So we know that if I have 1 over 1 minus x, this is going to be the sum from 0 to infinity of x to the n power. That's the geometric series, and it converges to 1 over 1 minus x. So we can actually transfer this to look like that. So that's what we're going to do here. Make it look just like that. So this is equal to 1 over plus 2x. I can write it as minus 2x. Once I have done that, I know this is going to be the sum starting from n equals 0 to infinity of some x to the n power. And my x is going to be this new input, negative 2x. And then we simply simplify the formula and start writing out a few terms. We want the first 5 terms for this particular Maclaurin series. So let's go ahead and simplify this. So this is equivalent to, right, the sum starting from n equals 0 to infinity of negative 1 to the n times 2 to the n times x to the n. So this is the series form. Now let's go ahead and write down 5 terms of this series. So for the first term, we're going to let n equal 0. So when n equals 0, you'll have negative 1 to the 0, which is 1, 2 to the 0, x to the 0. Everything is just 1. And then for the second term, when n equals 1, you're going to have negative 1 times 2 to the 1. So that will just be 2. So I'll write it like this, negative 1 times 2, x to the 1 power. So that will just be negative 2x. And then when n equals 2, you're going to plug in 2 for n. So you'll have positive 2 squared, that'll be 4, x to the second power. And then when n equals 3, you're going to get negative 1 times 2 to the third power. So I'm going to write it as negative 8 times x to the third power. And one more term, so then that will be for n equals 4. That'll be positive, negative 1 to the positive 4, that'll be positive 1. And then 2 to the fourth power, that'll be 16, x to the fourth, plus dot, dot, dot. Of course, there are more terms. We just need first 5 terms. So that will be our answer to part A, the first 5 terms of this series. Now for the second part, we're going to find the first 4 non-zero terms of the derivative of this function that we just computed as an infinite sum. So here's part B. So we know that f of x, that's from above. So we know f of x is equal to that infinite sum. So that means f prime of x, we're going to take the derivative of f of x. That's what f prime of x is. And f of x is this infinite sum. So I'm going to replace it with that infinite sum. So this will look like this. So you're taking the derivative of the sum starting from n equals 0 to infinity of negative 1 to the n times 2 to the n times x to the n. Or you can think of as taking the derivative of these pieces right here, term by term, right here. So you can take the derivative of these guys term by term. So you can take the derivative of the formula or each term, you'll get the same thing. So I'm going to go ahead and take the derivative of this formula right here, and I'll show you that it's equivalent to taking the derivative of these guys term by term. So let's go ahead and do that. Take the derivative of this sum. So assuming convergence, it is convergence on some interval. So you can figure that out on your own by applying the ratio test. We're going to go ahead and simply start taking the derivative. So when you take the derivative, take a look at this piece right here. When you take the derivative of 1, that's going to disappear. And then you start taking the derivative of the second term, which means our sum is going to start at 1 and then just go to infinity. So that this term will disappear when you take the derivative. We're going to start right here. That's where our sum will start. So then the derivative of this formula right here, it's going to be, so all of these are constants. You just carry them with you. So we're taking the derivative of x to the n with respect to x. So you bring down the power times x to the n minus 1. So that will be our formula for f prime of x. Now let's check this out with these pieces right here. If you take the derivative of negative 2x, you get negative 2. Plus, when you take the derivative of this, you get 4 times 2, that will be 8x. When you take the derivative of that, you get negative 8 times 3, that'll be negative 24x squared. And then the last one, you'll have this one right here, plus 16 times 4, that will be 64x to the third, and so on. So there you have your 4 non-zero terms of the derivative. So we got it just by differentiating the formula, or you can also differentiate term by term and you get the same formula. So this will be the answer to the second part. Now for the next part, we're going to approximate. So I'm going to just go ahead and copy this on the bottom so it is easy access for us. Okay, so for part C, we're going to take the answer to part B, which is right here, and we're going to approximate the derivative at 0.05 with an error not exceeding this much. And we're going to verify our answer. So here we're actually going to use the alternating series estimation theorem. So let's go ahead and plug in 0.05 into our derivative. So I'm going to convert this to a fraction because it's easier. So this is the same thing as looking at the derivative at 5 over 100, which is equivalent to say this is the derivative at 1 over 20. So let's go ahead and plug in 1 over 20 into every x. So you can plug it in here into the formula, write out the few terms, or you can just plug it in here. I'm going to go ahead and plug it into the expanded form because it's easier. So we have f prime of 1 over 20, that's equal to negative 2 times, negative 2 plus 8 times 1 over 20 minus 24 times 1 over 20 squared plus 64 times 1 over 20 to the third, and so on. Now we want to make sure that our sum is no more than 0.01. So this is equivalent to 1 over 100. So we want our error to be no more than 0.01. So let's see which one of these, what less than 0.01. So if you simplify some of these terms, this is negative 2. Now 8 over 20, that can be simplified into 2 over 5. And then 24 over 1 over 20 squared, that's simply 24 over 400. And then can be simplified into 6 over 100. And then the last one, I'm just going to keep it as 64 times 1 over 20 cubed. So that's about 8,000. All right, and just keep on going. So I'm going to see which one of these will be less than 0.01. So if you take a look at this one right here, this is about 0.4. So this is 0.4. So that's definitely greater than 0.01. This one right here, this is about 0.06, which is greater than 0.01. And this right here, this is going to be about 0.008, which is less than 0.01. Now, once you find that number, so this guy right here, once you find the number less than your error, you add up everything before that. So which means we're going to conclude that our sum is up to these guys right here. So these are the ones we're going to add up. So our derivative at 1/120, it's going to be the sum of -2 plus 2/5, that's 0.4, and then 6/10, that's 0.06. And this will give us approximately -1.66. So once you find out the term that is less than the error you're looking for, you add up everything before. So this is our approximation for the derivative at 1/20. Now, how good is this approximation? Is it within the error we wanted? Well, yeah, right? Because it's less than this term right here. So we're going to verify that our error in absolute value is less than the term after a sub n. So that'll be a sub n plus 1. We wanted that to be less than 0.01. It's going to be a fourth term, which is less than 0.01. And so 0.008 is less than 0.01. So checked. So we have the accuracy that we want.